Hello everyone, I'm Dr. Alok Agrawal and I welcome you all on the fifth lecture of fluid mechanics having course code ME404. So in this lecture, we'll continue what we have learned in our last lecture, that is viscosity. So in last video, we have seen that what is viscosity, and we have also derived a very small relationship, that is Newton's law of viscosity. Now we will see what are Newtonian fluid and what are non-Newtonian fluid. So, a fluid in which there is a relationship between shear stress and shear deformation is linear, or the fluid which obeys the Newton's law of viscosity is called Newtonian fluid. We have derived Newton's law of viscosity, that is tau is equal to mu du by dy. So the fluid which follows that equation is known as Newtonian fluid, or we can say that in which there will be a linear relationship between the shear stress and shear deformation. And the type of fluid which does not follow the Newton's law of viscosity is known as non-Newtonian. Or we can also say that the fluid in which there is not a direct relationship between shear stress and shear deformation, which is that is called non-Newtonian fluid. Okay. So now let us move to the unit of viscosity. So we have seen that tau is equal to mu du by dy. So in order to derive the unit of viscosity, we have to keep this viscosity mu in one side and rest of the thing on the other side. That is mu is equal to tau dy by du. Now this tau is shear stress, which can be written as force upon area. Okay, so here we have written force upon area. Dy is length, that is distance between the two players, which can be denoted by length, and du is velocity, difference between the two layers, that is velocity. So when we write the unit of each one, that is force Newton, area meter square, dy meter, du meter per second. So after solving it, we get unit of viscosity as force into time by length square, that is Newton second per meter square, which is the SI unit of viscosity. And the CGS unit of viscosity is dyne second per centimeter square, which is also called poise. Okay, so there are two units of viscosity. SI unit is Newton second per meter square, and CGS unit is dyne second per centimeter square, which is also called poise. And there is a relationship between these two units, that is 1 Newton second per meter square is equal to 10 poise. This relationship is very important because we will use it for solving different problems. Again, very important information. Why we have given name to this CGS unit, because viscosity of most of the fluids is very low. Okay, that can be seen that viscosity of water is 0.01 poise or 1 centipoise. So generally the viscosity of fluid is given in terms of CGS unit, because that SI unit is quite bigger for defining the viscosity of any fluid. Now the temperature dependency of viscosity. How viscosity vary with temperature, because here we have seen that when saying the viscosity of water as 1 centipoise or 0.01 poise, I am also saying the temperature. It means that when we change this temperature, the viscosity of water will change. So viscosity depends on the temperature. So change in temperature had different effect in viscosity when we talk about two different fluid, that is liquid or gas. So let us see first what effect the change in temperature will give to the viscosity of liquid. So viscosity in liquid originates because of the intermolecular force of attraction. Okay, and at higher temperature there will be a vigorous random motion takes place with respect to their mean position. The molecules of liquid will start moving with very high speed or very high velocity. Okay, thereby they weakens the intermolecular force of attraction. The intermolecular force of attraction between the molecule decreases, and when this intermolecular force of attraction between the molecule decreases, what will happen? there will be a decrease in viscosity. Okay, they will cause less resistance to the adjacent fluid. So we can say that when we increase the temperature of liquid, any liquid, what will happen? The viscosity of that liquid will decrease. But what will happen to the gas? In gas, the intermolecular force of attraction does not dominate the viscosity, and viscosity generally originates because of the transfer and exchange of molecular momentum. And when we increase the temperature, the molecule of gases will have more random motion, and because of that higher random motion, there will be a chances of increase in collision, and there will be a higher exchange of molecular momentum at higher temperature. And because of that, there will be a more resistance for the movement of the molecules. So for gases, what will happen when we increase the temperature? The viscosity of gases increases. So these two lines are very important, that if the temperature of liquid is increased, the viscosity decreases. Whereas when the temperature of gases increases, the viscosity is also increases. Next, very important, kinematic viscosity. This is important because in more we will see that this will be helpful for us for solving various numericals. So now let us see what is kinematic viscosity. It is very simple. It is defined as the ratio between dynamic viscosity and density of fluid. We have seen dynamic viscosity, which is also known as coefficient of viscosity. So kinematic viscosity is when we divide this dynamic viscosity by density of that fluid, we will get kinematic viscosity, which is mu by rho. Okay, so in order to know the unit of viscosity, again we have to write the unit of dynamic viscosity and the unit of density, and when we'll solve it, we'll get length square by time, which is meter square per second as SI unit of kinematic viscosity, and centimeter square per second as CGS unit of viscosity. Again, this CGS unit of kinematic viscosity is also known as Stokes, and there is a relationship between these two, that is 1 Stoke or 1 centimeter square per second is equal to 10 to the power minus 4 meter square per second. So this kinematic viscosity is the ratio of dynamic viscosity by density. Okay. So again, why we are giving name to this CGS unit as Stoke, because most of the fluid having kinematic viscosity which is very low value, and in that case generally we not use SI unit, we generally use CGS unit for those fluids. Okay. So this is about kinematic viscosity. So in today's class, we have seen that what are fluids, okay? What is dynamic viscosity unit? We have seen what are Newtonian fluid and what are non-Newtonian fluid. Again, we have seen what is kinematic viscosity. One more thing is left, that is types of fluid. That is also very important, which is asked in exam. So generally, we have 5 types of fluid, that is ideal fluid, real fluid, Newtonian, non-Newtonian, and ideal plastic. Out of this, these 4 are of more importance. So what is ideal fluid? Ideal fluid is a hypothetical fluid which is no existent. Okay, this is an imaginary fluid. Ideal fluid is defined as an incompressible fluid. Any fluid which has incompressible and having no viscosity is known as ideal. And in actual, there is no fluid having zero viscosity. So this ideal fluid is a imaginary fluid, and in this graph of shear stress by velocity gradient, that is tau by du by dy, this ideal fluid is represented by a horizontal line having shear stress 0, because when we keep mu is equal to 0 in Newton's law of viscosity, we get tau is equal to 0, and this tau is equal to 0 is only in this velocity gradient line. The second one is real fluid. A real fluid is a fluid which possesses viscosity. Okay, so all fluid in actual practice are real fluid. Now this real fluid is again divided into different type of fluid, that is Newtonian fluid, non-Newtonian fluid, or ideal plastic. A real fluid in which shear stress is directly proportional to the rate of shear strain, we called it as a Newtonian fluid. Or we can say that the fluid which follows Newton's law of viscosity are known as Newtonian fluid, and we get a straight line, equation of line that is represented as this. Another is non-Newtonian fluid. It is a real fluid in which the shear stress is not directly proportional to the rate of shear strain and is known as non-Newtonian fluid. Again, it is also defined as the fluid which does not follow the Newton's law of viscosity is called non-Newtonian. The next one is ideal plastic fluid. Ideal plastic fluid is a fluid in which shear stress is more than yield value and the shear stress is proportional to the rate of shear strain. Here see, the shear stress is proportional to the shear strain, but also the shear stress is more than the yield value, and this is known as plastic fluid. So when there will be a question in exam that what are the different types of fluid, we have to define these 5 types of fluid with this graph between shear stress and velocity gradient. Okay, so in next class we will solve few problems related to the viscosity. Okay, thank you very much.